Morning, everyone. All right, nice to see you all back after the 1 week break. All right, so today's lecture onwards, we are going full swing into the RTOS development. All right, and today's lecture is the first one, so it's going to be an interesting lecture. And as usual, I will demonstrate the lab 6, okay, where we are going to look into how a multi-threaded program actually works. Okay, and then you will get to see how we create the project, how it works, and some very important concepts. Okay, so today's lecture, we're going to cover the important fundamental concepts of the states of the OS. All right, and once you get that part clear, okay, the rest of the concepts will be easier to understand. Okay, so the first step is always understanding the states. All right, and that is what we're going to be focusing on today. Okay, and then I also talk a bit about the midterm and the project as well later on. Okay, so let's get started. Okay, let me share my screen here. Okay, can everybody see my screen? Okay, thank you. Okay, so in terms of lecture material today is not so much, all right, because I want to focus on making sure you understand the concepts well, all right, and that concepts we're going to again probably reinforce when I go through the lab demo, okay, and then you get to see it in action. All right, so let's get an overview of operating systems, okay, and why we sort of need them or why they help us, okay, in the context of embedded systems. All right, so in terms of operating systems, there are many components to it. All right, so of course, one of the first thing is process management. So when you talk about process, okay, it's about running multiple activities at the same time. So when you are doing that, of course, how do you allocate resources? Okay, so those are some of the important things that the OS has to take care of. How do you manage the memory, right? Because your system has a finite amount of memory, right? And you have so many sort of parallel processors trying to use this memory. So how do we allocate to all the different processors that want memory? How do we protect it, and so on? And we also have a separate lecture specifically on virtual memory as well. All right. Then file systems. All right. So file systems is basically every OS has some ability to manage its data. All right. Of course, normally you can say that in embedded system context, most of the time we can just keep the data we want within the program itself. All right. But when we want to keep the data in a sort of permanent storage even after I power on the system, so you need to have some other mechanism. All right, so you definitely need a permanent storage capability, and you also need a way to manage that storage with the file system. All right, so that is also another thing that the OS has to manage. Okay, input output device drivers are of course the most basic one, because like the GPIOs, the PWMs and so on. So whatever your system is supposed to have, you should be able to control that even at the OS level. Okay, then the other three, network, security, and GUI. So network, I think all of us know, okay, connectivity, Wi-Fi, and so on. Security is again depending on what layer of security you're talking about. Could be hardware layer, could be the internet protocol layer, and so on. Okay, and then the GUI itself. So in terms of the GUI, again, some OS libraries and so on, we already have some sort of packages to help you with quick GUI development, right? So these are many things that the OS has to handle, and because we use the OS, okay, we will see that some of these things can actually be done a lot more easier, okay, with the OS than without the OS. All right. So an operating system in general has to deal with a lot of things. All right. And the main idea is we have multiple processes that are running. So what is a process? A process, okay, you can think of it as a application. Okay, in a very easy way to look at it is, for example, you use your phone. Okay, so when you want to make a phone call, So that will launch a process that manages the phone call. Correct. When you launch your browser, that is a separate process to use the browser over the internet. Okay, when you launch your GPS, okay, then that's a separate process to use the GPS module and get some information. So you can have an operating system is supposed to be able to handle, okay, multiple processes running in parallel. Correct. So there's a lot of things that happen in the background, okay, that are not really visible to us. Okay, but as long as the OS is managing it well, then at the front end, the user should not experience any issue. All right, so at the back end, the OS must be able to do all of this stuff, okay, like what we said just now. All right, and we are going to be looking into all of this along the way. All right, so how do you create tasks? Okay, how do you schedule them? Okay, how do you allow them to communicate with each other? Okay, how do you allow concurrency? Okay, parallel processing. All right, and as I mentioned, what we want is we want the whole process to be the user application to be abstracted. Okay, so when you say abstracted means when you are writing the application, you want to be focused on the whole front end of it. Okay, while you know that the OS is handling the back end of it. Okay, so it's simple, right? Just like for example, if like when you did your lab 5 with the UART over the Wi-Fi, okay, you take it that the Wi-Fi module, okay, the library will handle that back-end Wi-Fi communication for us. Right, so we handle the front end of making sure that we configure it correctly, we send the data, we receive the data. Right, the back end of the actual Wi-Fi, the IP address, the protocol, all of that is handled at another layer. Okay, so we take it that that layer is correct. Okay, so we focus on the front end to develop the application. So same thing for a process. A process, when you develop a process, you want to have the confidence that the OS is running as expected. So as long as you use the OS correctly, then everything should happen as expected. Okay. So memory, again, we have limited amount of memory. Okay, one for the code, one for the data. Okay, and you want to make sure that the OS is able to support that. All right, so the concept of the virtual memory and so on, we will cover in a separate lecture later on. So we'll get into more details. Okay, files and IO. Okay, so like I said, files is just a way to handle the information, okay, bulk information, especially when you want to keep it even when your system is powered down. All right, so you need a file system. And IO is basically what we have been doing so far, right, and something you're familiar with. So the operating system again has all these different components, but at the same time they need to be able to interact with each other. All right, so when you create a process, the process must be able to interact with the file system, must be able to interact with the memory, must be able to interact with the GUI and so on. All right, and you need to make sure that everything sort of works together seamlessly. All right, and one of the challenges is, of course, you want to make sure the OS itself is reliable. Okay, it's backwards compatible. Okay, so sometimes especially in commercial OS environment, the OS can get upgraded, so you still want to make sure that it is sort of compatible with what you've already done before in the past. Correct. Okay, it's extensible. Okay, that means you can easily plug and play maybe different modules from other libraries easily into your OS, and it's also portable. Okay, so in a sense, portable means you want to be able to have some flexibility to say that whatever code you are writing, you can take that baseline architecture and port it to a different platform. Okay, so for example, in this project, you're working on, we're going to be doing the RTX RTOS. So that is the OS, correct? We are going to be learning RTX RTOS. Now, in our module, we are of course running this on the KL25Z. Okay, which is a ARM Cortex, okay, M0 platform, M0 plus platform. Okay, but in reality, of course, in the industry, you don't stick with one controller, one platform throughout the entire lifetime, right? You may upgrade, you may change, correct? So maybe later on the company says, okay, we don't want to use this Cortex M0 plus, maybe we upgrade or we change to maybe M3, okay, some other microcontroller. Okay, then is RTX still going to be compatible with M3? All right, so that is an issue. Or if you move away from ARM altogether, correct, and then you decide to go with some other sort of processor platform, all right, then is your RTX already ported over to a new platform. So you want to look into portability, okay, especially if you are in the industry and you are thinking about long-term use of a particular OS. Okay, so again, these are things that will usually be supported if it is a commercial OS. All right, because in a commercial sense, once you have invested money, the company also has to make sure that they are supporting you to a certain extent. All right, so now it comes to this concept of real-time operating system. So what is the difference between what you call a OS and a RTOS? All right, so the fundamental concept is the same. All right, that means the baseline OS concepts are the same. The key thing is this idea of real time. Okay, so when you say real time, means you are able to meet some deadlines. All right, so of course, not all deadlines need to be really met by that specific time frame. So that is why we have this concept of a hard real time and a soft real time. So when you say a hard real time means you have to ensure that a particular task is completed on time. Okay, whereas a soft real time means if you have a deadline in mind when you create the architecture, but if you are not able to meet it, do you still go ahead to do the task? Correct. So these are some of the two sort of variations of deadline. Okay, so a simple example I give you is, for example, you are driving a car. Correct. So if you are driving a car, all right, and you press on the brakes, okay, you expect the ABS system to kick in and stop the car. All right, so that is a hard real time. It has to respond and stop the car within the time that the designers have sort of enforced. All right, so you have to do it. So if you cannot sort of apply the ABS and stop the brakes, and apply the brakes and stop the car in time, then that is considered a failure. Correct, system failure. Okay, a soft real-time system is anything else that is not so critical. For example, in the same car context, maybe you change the aircon control temperature, okay, or you're trying to change the music, okay, some settings. So these are things that are not really time critical, correct? If you change the aircon setting, whether it responds in 1 second or responds in 2 seconds, it still doesn't make much of a difference. So it is still fine if you don't meet the deadline. Okay, so a hard real time is something that you have to fulfill. Okay, if not, system failure can occur. All right, so that is where the idea of the RTOS comes in. That means you want to have some high level of predictability, okay, and determinism, okay, when it comes to specific tasks. All right, now the common misconception, okay, that most people have when they first think about RTOS is this. Okay, is real time equals to fastest response. Okay, so the answer here is definitely a no. Okay, real time is not the fastest response. It is being able to respond within the deadline. Okay, so if I press a button and I expect the LED to light up in 1 second, then 1 second is my deadline. If I say light up in 1 minute, then 1 minute is my deadline. All right, so it can be a very fast or short duration deadline. It could be a very long deadline. Okay, but as long as I can fulfill my timing deadline, okay, then you are still considered a real-time system. You're fulfilling the real-time requirements of the system. All right, so that is the key thing. All right, and of course, you also want to have some fail safety. All right, that means in the event that you are not able to fulfill some deadlines, okay, something is going wrong, okay, what should you do? All right, of course, it doesn't mean you just shut down everything. All right, maybe you need to have some way of recovery. Okay, how do you recover the system back to a safe state and start over again? Okay, so these are things that you can also think about, all right, in a real world context. All right, and of course, an RTOS demands a lot of scheduling and memory allocation, so we will look into how the RTX does it in our case. Okay, so of course, when you read some books and so on, they will generally talk about RTOS. Some of them may also call it EOS, okay, embedded operating system. Okay, they are in a sense interchangeable, okay, because the whole idea of RTOS came about because most of these real-time requirements are in embedded devices, correct? Because in general purpose systems like your computers, okay, your laptops and so on, you don't really have any real-time deadline, correct? Because if you click on Microsoft Word, sometimes it opens up within 5 seconds, sometimes it takes 30 seconds and so on. Okay, but either way, you will still use it. Okay, you're not going to throw away the laptop just because it took 1 minute to open up the Microsoft Word. All right, so you will still accept it, you will still use it. All right, so you do not think of it as a major system failure, correct? In a general purpose computing concept. All right, whereas in an embedded OS, embedded system context, you are more particular about the timing response. All right, so for example, if you take, I mean, nowadays we use GPS on the phone, all right, but before that, there were a lot of this dedicated GPS devices, correct, that cars used to have. Okay, so if you have a dedicated GPS device, which is a embedded device running an OS, you expect that real-time response, correct? You do not want to be driving and then the voice says, oh, you should have turned right 5 minutes ago. It's too late already, correct? You should give you some advanced notice that, okay, 500 meters ahead, turn right, something like that. Okay, so that real-time response is sort of inherent in the expectation of embedded systems. So that is why you see that in some literature or books, you may see the use of EOS or RTOS interchangeably. Okay, but the concepts are the same. All right. And in terms of the embedded OS, definitely the GUI and security are things that are sort of application specific. Okay, if you think you need it, then you can integrate those OS libraries inside, okay, and work on the project. Okay, so the whole idea of RTOS, okay, on embedded system is basically so that we do not need to be limited by the super loop. Okay, so if you recall the super loop concept that we had, okay, where we had the pothole detector, okay, where you have the GPS decoding and then checking the tables and then updating the tables and so on. So that there's a lot of uncertainty when you have this super loop, okay, because data might come in at any point of time, you need to process that immediately and so on. Okay, so this RTOS on embedded systems, whole idea is to sort of make sure we can get past this super loop, okay, and have a way to encapsulate the information that we want, that the things we want to do into tasks, okay, and schedule them based on some form of a demand. All right, so this helps us to have a much better program flow. Okay, the overall structure of your program will be much better, and most importantly, you have a more deterministic response. Okay, previously, if you look at the super loop approach, okay, the deterministic part was when we use ISR. Okay, but again, ISRs are limited. Okay, and you may not necessarily have ISR for everything that you want to do. All right, and even with ISR also, you still have the limitation of only doing some limited amount of work there. All right, and the rest of it has to go back to the main loop. All right, so there's still a lot of this unpredictable timing behavior with the super loop. Okay, whereas with the RTOS, you sort of are able to manage all of that much better. All right, so that is what we're going to be seeing. So for the RTOS for this course, okay, we are using the KL All right. So RTX is a commercial OS, all right. So it is used in the industry, all right, and it supports ARM Cortex M-Cores, and is a well-rounded RTOS for embedded systems. Okay, and the so the RTOS, the structure we will go through, okay, along the way, and the API you'll be using is what we call the CMSIS RTOS API. All right, so later when I'll share the link with you all, where all the documentation is online. So when you are writing your code and all, you can refer to the online documentation for reference. All right, and that gives you a very nice way of developing your code and structuring it, okay, to fulfill the requirements. Okay, so before we go on to the next chapter, all right, I just want to take a quick poll, okay, on your hardware development so far. That means in terms of putting together the robot, the staff and so on. Okay, so the majority of you say what hardware is. I don't know whether it's a joke or it's real. All right, but if it's real, then it's a cause for concern. Okay, so I hope over the next 1-2 weeks, this week and next week, you try to catch up on your hardware part. Okay, trust me, as the weeks go by very fast, you'll get very stressed towards the end. Okay, trust me. Okay, I have seen students on the day of the presentation, they are there soldering the driver chip. Okay, the connectors. Okay, so you can't make it like that. Okay, trust me. Okay, and as I said before, we do not have all the weeks. The last week, which is the final week for the presentation, you do not have access to the lab. Okay, you need to submit your robots. Okay, at the start of your lab slot. Okay, and then you will call you in for the presentation. Okay, so you only have up to the second last week to do your development. Okay, so your time is limited. All right, so I hope you catch up with your work. Okay, for this hardware development part. Okay, so let's move on to the next chapter. Okay, give me a minute here. Okay, so the first lecture is just, the earlier lecture is just to introduce you to the basic idea of the OS. Okay, now we're going to go one step into the actual sort of syntax and the idea behind how process management is done in the OS. All right, so this is quite an important topic, all right, because again, the idea of how a process is managed, okay, at the OS level is important, so we understand what is really happening in the background. All right, then only when we are going to write the application, we are able to know which approach to take. All right, so we're going to talk about the process. What is it? Okay, we're going to look at the memory layout a bit. Okay, and how switching is done. Okay, between processes. Okay, these are the three main things. Okay, and then you'll be looking at some examples. All right, and the process termination as well as context switching. So this is the key thing. Okay, where you need to understand what is the idea of context switching and how that allows the whole multi-threading environment to function. Okay, so what is instance of a running program? So a process, okay, when you say we create a process, basically we are creating an instance of a running program. All right, so just like how you can open up a few different MS Word or PowerPoint or browser windows. Okay, so and each of them has its own space. Okay, so if you open up, okay, your task manager, okay, your activity monitor, okay, you will see that, okay, for example, here I can open up the Macrovision 3 times. Okay, 3 different instances of it, and each of it I can be running at the same time, and each of them have different applications or different projects running in it. Okay, why is that possible? Because when I run that application, I have an independent memory for each process. All right, so each time I open, I use some memory from the system and run it independently. Okay, so a process, okay, that's the concept of the process. That means you create an instance, okay, of any particular program that you want. Okay, and that instance has its own space, its own memory, and so on. So it does not conflict with any other process that is also running the same program. Okay, so that is the idea of what a process is all about. Okay, so when you create a process, okay, you are basically trying to say that I want to now run some application, and I want to, of course, to do that I need the CPU, right? So I need to have some CPU time allocated to me to run the process. All right, so that is the whole idea of the OS. So it sort of takes the whole CPU and in a sense gives you a virtual CPU. Okay, so in a sense virtual because it gives you a part of the CPU each time. Okay, it is still the actual CPU, but it gives you a part of the CPU at different time slots to allow you to run your application. Okay, and since you are having this application, you also need some memory. Okay, and since the OS has to manage multiple processes. Okay, so since it has to handle multiple processes, it needs to be able to uniquely identify the process. So that is where the process ID is allocated. And within the process, you may also have multiple threads. Okay, so the idea of process and threads, okay, it is again another sort of sometimes you can get a bit confused. In some books they use process all the way, some books they use thread all the way, or in some of them they may use tasks all the way. Okay, so the idea is very similar. Okay, but in general OS context, what they will usually say is process is the higher level sort of instance that we have created, and that process may launch separate tasks, okay, to do something more specific to some activity. Okay, so for example, okay, you open up your browser. Okay, so that is a process. Okay, but in the browser you go to YouTube and you start to watch a video. So when you start to watch a video, okay, what do you need? You need to open up, okay, some network tasks to handle the video streaming. Then you need to open up some tasks to handle the video display on your monitor. Then you need to happen to also open up some tasks for the audio playback and so on. So a process is the general application you run, but that process may inherently sort of instantiate other tasks to handle some of these sub activities within the process. Okay, so this is the general terminology. All right, in our context, okay, we will treat them as similar. That means you can call it process, you can call it task, you can call it thread. Okay, the idea is the same. Okay, eventually one task can create multiple tasks, one thread can create multiple threads, and so on. Okay, but the idea is the same. Okay, and the whole concept is that the operating system tries to create this illusion, okay, that a process is running by wholly owning the CPU. Okay, so when you open up or launch a process, as far as the process is concerned, it is able to fully use the CPU and the resources and do whatever it needs to do. Okay, so it sees a dedicated processor and it sees some allocated memory, okay, where it can use and do whatever it needs to do. Okay, but at the same time, there is also this concept of inter-process communication. All right, that means there is a way, okay, there is a mechanism in place for tasks to talk to each other. So, for example, the video task and audio task can talk to each other. The network task and the video task can talk to each other, and so on. Okay, so there is also a framework for multiple tasks to communicate with each other using the OS as the backbone. Okay, so these are again all the sort of features given to us by the OS. Okay, so this is just a single slide to just give you an idea. There will be another lecture where we dedicate to understanding the memory layout. Okay, but in general, okay, our memory is given in this sort of layout where your code and text is sort of allocated to one chunk. Okay, normally it is usually in the lower or upper region of the memory, okay, depending on how your architecture is designed. Okay, and this is usually what you read from the program. Okay, the code and the text followed by some initialized data. All right, and then the data itself you can have initialized or uninitialized. All right, so you have the concept of static data and so on. Okay, and then you also have heap and stack. Okay, so the heap and stack is used, okay, for memory allocation while the program is running. Okay, heap is generally used for malloc and free, whereas stack is used for your procedural calls. Okay, when you jump to a function, you return, okay, to save the information on the stack and pop it out again later on. Okay, again, this is just to give you a rough overview of how memory is organized in a program. Okay, this is of course just an overview. Okay, we will go into more details at another time. So this is basically sort of what we need, all right, when we are running a program. So as far as the process is concerned, okay, while I'm switching between operating system, I need to be able to keep track of the context. Okay, that means when I'm running a particular task, task 1, and I have another task, task 2, okay, while I'm running, I may have to switch to task 2 to run, and then I may have to switch back after that. So as I'm switching to and fro between multiple tasks, I need to be able to know exactly where I left off. So what was I doing over here? Okay, what were the contents of the memory? What was the CPU state, the OS state, and so on. So all of this information needs to be stored. Okay, to be stored somewhere. All right, and at the same time, when I return, I should be able to continue from where I left off. All right. So that is the idea of the process abstraction. When you are writing the task, okay, when you're writing the application, you do not think about this context switching. All right. You do not think about what is going to happen in the background that is beyond what I am focusing on. Okay. Just like when you are running when you open up your Microsoft Word to write something, to type something, in the background, you can be playing music. Correct. But your MS Word does not keep track of what you're doing at the back end. As far as the application you're focusing on is concerned, it makes sure that it is functioning according to what you have written. It is the OS responsibility to make sure that while the user is using this Word application, the second application, which is the audio player, is still able to run without any disruption. So that is the OS responsibility. Okay, so that the front end task creation is focused on that particular objective alone. Okay, so that is why we call it the abstraction. So each process is written at an abstract level. That means you focus on that particular task you want to do. Okay, but again, like I said, there will be cases where you want tasks to communicate with each other. So in those contexts, you will want to be aware of what is happening in another task. Okay, is certain things done already? Is certain things completed? Okay, can I carry on and so on? So that part we will look at that when we study about the inter-process communication. Okay, so this is the process control block that holds all the information related to a particular process or task. All right, so this is basically the snapshot of everything that your task is currently performing. And this information is critical because when you are doing that context switch from one task to another task, and you're going to come back. Okay, so this is where you save before you switch, and when you want to return back, you reload from this control block. Okay, and this control block holds all the information you need. Okay, things like your program counter, your stack pointer, your other registers. Okay, all this other information. Okay, your scheduling, your memory, and so on. So all the information related to a particular task is stored within its own control block. So that is what the OS is always looking at when it does a context switch and it decides whether a particular task is supposed to, or when a particular task is resuming, okay, after a context switch, where should I start from? How do I carry on? How do I reload all the registers and so on? All right, so this is giving an example, okay, of a control block in the RTX. Okay, so of course it has a lot of information. All right, but I think what we want to be currently focused on is these three. Okay, one is the task state. Okay, so the task state gives us a sense of where I am and what am I allowed to do or what am I waiting for. So that is the state of the task. The other one is the priority. Okay, so when you create a task, you can also specify priority. All right, and that sort of again gives us some idea of which tasks are more important than others. All right, and then the third one here is the task ID. This task ID is the one that is used, okay, to keep track of the particular task within the OS. Okay. Now let's look at the whole idea of the process creation. So when you create a process, what happens? Okay, when you create a process, you are assigned a new ID. You are allocated memory for the process control block. Okay, and the process control block is initialized and is linked in the queue. That means the OS, okay, basically what it does is the moment you create a new thread, okay, so if I create a new task one, it will also create with it its own task one process control block. Okay, and this process control block will now be part of the management under the OS. Okay, because now the task OS is also supposed to manage task one. Okay, because you have created this new process or new task. Okay, and of course, once you terminate the task, you will sort of release all the resources, okay, that it was holding on to and reclaim back the memory. So the OS will reclaim back the memory. All right, so this process termination is again in our general purpose OS context is equivalent to just closing the maybe browser or closing the Word or PowerPoint application. Okay, so you terminate the process. So the memory is freed back to the OS. But in an embedded system, okay, you generally write processes that never terminate. Okay, because things are supposed to run indefinitely in an embedded systems context. All right, and usually when you say a process gets terminated, sometimes it could be that something went wrong. Okay, so in our embedded system context, we generally do not terminate any task. We create it and we keep it running in an infinite loop. Okay, so we will look at that later. Okay, in the lab demo. Okay, so in terms of the context switching, again, the whole idea is the process control block. Okay, makes it easy for us to hold everything that we need to hold the information related to a particular task. Right, so these are all the stuff, the registers, program counter, memory state, and so on. So this idea is similar to the main loop and interrupt context. Okay, so for example, in our super loop, your main loop is running and you have an interrupt. Okay, and then you finish and you come back. All right, but in that super loop context, the only thing we save is some register information, okay, and the return address. Okay, so some registers and the return address. All right, and then we can go to the interrupt and then we can come back. All right, but in the OS, you have a lot of other information related to the whole task. Okay, so all of that information will be saved onto the process control block of that particular task. Okay, and if I'm restoring from another task, then or if I switch to another task, then I restore the state from that particular PCB. Okay, so the process control block, okay, is the one that is critical to hold the information related to any particular task. Okay, and as you can see here, there is a delay over here. Okay, so every time there's a context switch, it does take up some time. All right, so again, all of this is done in the back end, okay, by the OS. Okay, so it is sort of transparent to us, right? But it is happening many times, okay, with each task that you have. Okay, so now let's look at the process states. All right, so the process states gives us an idea of where it is exactly, okay, within its lifetime. Okay, so there is a cycle, all right, where it will go through. All right, and let's look at that now. So there are 5 main states over here: new, ready, okay, running, block, and exit. All right, so let's look at this. So these are all this is the state transition sort of table, okay, that sort of gives us the idea of the OS, all right, and the different states. Okay, so the very first one, new. Okay, so when it is new, it has just been created. Okay, so that is new. So when it is new, that means you have created the task, and of course before that the task is non-existent. Okay, but once you create a new task, then the OS allocates the process control block to it, and it now is part of the queue. Okay, so this queue, once it's part of the queue, all right, we call it in the ready state. Okay, now generally we say OS manages it, but the actual sort of framework within the OS is what we call the scheduler. Okay, so the scheduler, okay, within the OS, you can think of it as a manager, okay, that is in charge of looking at all the tasks that are ready. Okay, looking at all the tasks that are ready, and then selecting one of the tasks to use the CPU. Okay, so you have to understand that in our context, we only have a single CPU. Okay, you have a single CPU that can execute code. Okay, but you have a lot of tasks. Okay, task 1, okay, task 2, task 3, and so on. You can have many tasks that are currently in the ready queue. Okay, they're currently in the ready queue waiting for a chance to use the CPU. Okay, but only one task can use the CPU. So that is where the scheduler comes in. Okay, so the job of the scheduler, the responsibility of the scheduler is to select one of these tasks to use the CPU. All right, and the default approach to selection is by priority. Okay, so based on priority, it will select the task with the highest priority to switch. Okay, so let's say task 1 is the highest priority. Okay, so that task 1 will now get dispatched and switch to the run state. All right, so when I switch to the run state, okay, so within the process control block, the scheduler will update the information. Okay, then that task 1 has gone to run state. Okay, task 2 is still in ready state. Task 3 is still in ready state. Okay, so when task 1 is running, what happens? Okay, so it is doing something. Now, along the way, some things can happen. All right, that means, firstly, he can choose to have his own sort of what you call a timeout. Okay, you want to voluntarily give up the CPU for some time. Okay, so that is a voluntary giving up of the process. Okay, so that other tasks can run. Okay, so if that happens, okay, your task can now switch back to ready state. Okay, that means from run, it can now transition back to ready state. Okay, that is this part over here. Because that is voluntarily giving up the CPU. The other thing that can happen is you can go into what we call a block state. Okay, so some books may call it wait state. Okay, so when you say blocked or wait, okay, usually it is tied to some event. So what do you mean by event? All right, so this event could be that, okay, while you are running the code, okay, you wanted to do something, but you are unable to do it. Okay, a simple example is your task is running, okay, your task is running, and maybe along the way over here, it's supposed to send some data out to the UART port. Okay, it's supposed to send some data out to the UART port, but when it tries to access the UART port, it is not available. Okay, it's not available. So it wants to do some tasks, but it is not able to carry on with the task. Okay, so what it will do is it can go into what we call a block state. Okay, so the whole idea is task 1 is running, okay, but then it is now hit a wall where it cannot carry on. Okay, it is waiting for something. So since it's waiting, there is no point in it holding on to the CPU, all right, because we do not know how long it's going to wait. So what the scheduler will do is, since the task 1 is not able to carry on, it can now transition task 1 to the block state. Okay, so that is the block state over here. So it's not in the queue, but it is waiting. Okay, so when it goes to the block state, now what happens? The CPU is now free. All right, the CPU is now free because nobody else is using the CPU. Then the scheduler will come in again. All right, and the scheduler will come in and will look, okay, now who else is in the queue? All right, so I have task 2, I have task 3. Okay, so let's assume that maybe task 3 is the medium priority task and task 2 is the low priority. All right, so what he will do is he will dispatch task 3 to come here. Okay, so task 3 will now transition to the run state. Okay, now when task 3 is running, okay, along the way, the UART port suddenly becomes available. Okay, suddenly becomes available. Then what happens? Because task 1 was here, block, waiting for the UART. Okay, but now the UART is suddenly available. Okay, so when it's available, what happens is the scheduler, okay, will now be able to unblock task 1. So task 1 will now get unblocked and join the ready queue. So task 1 will come here. So it'll go back to ready queue. Okay, from the block state, you cannot go back to run immediately. The only person who can change you from ready to run is the scheduler, because that is the main manager overseeing all the tasks. Okay, so only the scheduler is able to transition you from the ready state to the run state. Okay, so when the task 1 that was blocked suddenly is able to access the UART, all right, it is now ready to run the code now. Okay, but the only thing that it can happen is it can transition now from the block state back to the ready state. All right, so once it goes back to the ready state, the scheduler will see that, okay, now task 3 is running, but task 1 is now back to ready, and task 1 is higher priority. Okay, and task 1 is higher priority. So because task 1 is now higher priority, I should let task 1 run. So task 1 should transition to run. Okay, now when task 1 transitions to run, where does task 3 go? Okay, now task 3 was running. Okay, it was happily running. Okay, nobody disturbed task 3, but unfortunately, a higher priority task came along. So since the higher priority task came along, okay, then the only option is for task 3 to transition back to ready. So task 3 will transition back to ready and again wait for its turn to run until a point of time when task 1 is not able to carry on, then task 3 can resume, and task 2 and so on. Okay, so you can see that this idea of context switching is very dynamic. Okay, it can happen many times, okay, throughout the entire lifetime of each task. All right, all depends on how you have written the code, what are the resources that it needs, okay, how are you managing the states and so on. All right, so all of this is happening in the back end. All right, so again, coming back to the important thing, when you write the front end application, we just need to be aware of the task state at each point of time, how the task is going to switch. All right, the events is what we need to focus on. The actual switching is handled by the OS. Okay, what we need to focus on is the events. Okay, what are the trigger points that will allow my task to carry on, or what will make my task go to a block state. Okay, so these events are the ones that we need to focus on, so we know when my task is going to transition from one state to another state. Okay, so effectively, you can see that this block here, this 3 points here is where most of the, this is where your task will be most of the time. Okay, the release is basically or what you call the exit state. Okay, when you release the task, you go into exit state. Again, this means you do not need the task anymore, so it's sort of terminated. Okay, but like I said, in general, in embedded system context, we don't generally terminate a task. Okay, so the only 3 states that we need to always focus on is the ready, run, and block. Again, understand the sort of context switching that is happening between them as and when events happen. All right, so this is a very important concept. Okay, so you need to understand that this thing is happening very dynamically, okay, in the background while your program is running. All right, and then when you understand that part well, then when you see what is happening, okay, on the board, in the hardware, then you can relate it back to this state transition picture here. Okay, so again, I will. Okay, so the question is, the priority is dependent on how much a task. You know, priority is assigned when you create a task. Okay, so when we create a task, we will assign the priority to it. Okay, this idea of priority switching is also there. Okay, that means a task that has to finish its activity within a closer deadline may be given a higher priority. Okay, but that is a dynamic priority, which we will cover some concept, okay, in a later chapter. Okay, but as far as our code is concerned, when we create a task, we can assign a priority to it. Okay, and it will stick with the priority, but the concept of dynamic priority I will cover in a later topic. Okay, so the process state, okay, this task control block is the one that holds this process state. And again, these are all the different states, okay, that are used by the OS to manage the state of the task. So even though I say the task is blocked, it could be blocked for many reasons. Okay, so that's where you have this variance of the block state. Okay, so it could be blocked because it's waiting for a semaphore, it's waiting for a mutex, it's waiting for some delay or something like that. All right, but again, we will look at all these concepts along the way, then you'll understand, okay, how it sort of comes together. Okay, so let me just make a quick midterm announcement. Okay, so similar to the announcement I sent. Okay, so we will have it in week 10. Okay, 20th October during our usual lecture slot. Okay, so it'll be a Luminous quiz, MCQ open book. Okay, so you can access your soft copy, hard copy material. Okay, but you strictly not allowed to do any form of internet searching or browsing, and at the same time, no access to any form of development or programming tool. Okay, so topics wise will be lectures 1 to 10, that means up to this week's lectures. Labs wise will be up to 1 to 7. Okay, 7 is only the first part of it, up to task priority, and tutorials 1 to 4. Okay, so besides that, I'll send out the instructions by this week. So the usual stuff is this too. Okay, the Zoom proctoring. Okay, I think all of you are familiar with it, and the screen recording. Okay, so I will be sending out a detailed instruction sheet. Okay, with all the important stuff. Okay, then of course the other stuff I think you also used to it is the Google Forms, correct? The Google Forms for the submission of questions, and the Google Docs for the clarification by me. Okay, so it's quite a standard. I think you're used to it from VPP already. Okay, so we are going to follow the same protocol. All right, and I think these are the important things here. Okay, so don't worry, I will send another announcement of it again next week. Okay, once I release the information preparation document. Okay, so we will go for a break now. Okay, after we come back from the break, we will look at this week's lab 6, okay, which is introduction to the RTOS and understand how to create and run the multi-threaded application. Okay, so let's go for a break now. Okay, I'll see you back here in 10 minutes time. Now it's 10 o'clock. Okay, 10:10, I'll see you back here. Okay, so welcome back. Let's continue. Okay, so there's a question there. What happens if I have a lot of tasks without any tasks terminating? All right, so you can create as many tasks as depending on the amount of memory you have. All right, so if you try to create tasks beyond your memory capacity, when you try to create it, it will already give you an error. Yeah, but if there's no error in task creation, then you can continue to create as many tasks as you like, and they can all be running concurrently. Okay. Okay, so let's go into the lab demo. Okay, so before that, let me share this link. Okay, so I'm sharing the link here in the chat. Okay, so this is basically the online documentation, right, for the RTOS and all the APIs that we're going to be using. All right, so this is a good thing to bookmark, okay, and keep it so that you know where to go to, all right, when you want to look up all of your RTOS functions. Okay, so let's get started looking at the lab first. All right, so in this week's or the lab 6, all right, so I know some of you are still catching up with the PWM and UART, okay, because one lab had to go online. All right, so no issues. If you are unable to do this week, you can still do it next week. All right, but again, this lab 6 is purely just you and the 25Z board alone. All right, so you don't need any other hardware. Okay, so even if anytime you're free at home with the board, also you can just run it. All right, as all of you have your own board. Okay, so in the first few steps of the lab manual, I show you the steps. Okay, how to create the RTOS project. Okay, this morning I uploaded another document on challenges with RTX 5. All right, so what we discovered, I think 1 or 2 batches back, was some students they did not install the IDE from the file that I gave. You downloaded some newer version. All right, and when you download a newer version of the KL IDE, the RTX project that you create seems to be slightly different as well. Okay, and it has some issues with running on the KL25Z board. Okay, so the other document that I uploaded this morning is to help you to sort of revert back some of the settings. All right, so you don't need to reinstall anything. Okay, if you have installed some newer version of KL IDE. All right, but this allows you to install or put the correct settings for the RTX so that you are able to run it without any issue. Okay, so the first thing is okay, when you create a new RTX project, okay, you will see the framework is a bit different. There will be a in the main program, okay, you will see that there is a system core clock update. Okay, so maybe I should open up the 6. Give me a minute. Let me open up the lab 6 manual here. Okay, so this is from your lab 6 manual. Okay, so when you create a new project, okay, based on the RTX 5, this is the template that you will start off with. All right, where you already have a main program. All right, and inside the main program, you will see 3 functions already, or 4 functions already there. Okay, the first one is your system core clock update. All right, so this is again part of the system initialization. All right, so we just we leave it as it is. So this is to allow the OS to get the correct updated information on the clock settings that you already have in your hardware. Okay, once that is done, then we say OS kernel initialize. So the OS kernel initialize to initialize the RTOS. So when you say initialize the RTOS, means it needs to do a lot of configuration at the hardware level in terms of the memory, the clocks, the resources it needs, and so on. Okay, so the OS first needs to initialize. Okay, and after you initialize, then you can call OS thread new. So OS thread new is to actually create a new thread. Okay, and by default, okay, the template already has a thread called add main. Okay, so you can use that. Okay, so it already creates a add main here, and the add main application thread is also written over here. All right, so when you want to create more threads, you can just add on after this line, and finally you can start the OS. Okay, after you start the OS, okay, you can see that the for loop is there, is an indefinite for loop. That means basically you never come back to the main after that. All right, so what is basically happening is when I initialize, okay, and I call OS thread new, I create a new thread in my system. Okay, so until this point, okay, until I say OS kernel start, I am still running in the single threaded application mode. That means line by line. Okay, but the moment I say OS kernel start, I am automatically switching from single threaded to multi-threaded. All right, so that is where the for loop here is just as a sort of safety net. Okay, that means if ever your OS fails, you come back to the main program, you are just stuck in that main loop forever. I mean the main for loop here forever. All right, so that is basically how your OS is functioning. All right, so to put it in context, okay, so basically what you have is your, okay, so when you first start the application, okay, you say kernel initialize, okay, and after you do the kernel initialization, okay, I mean the clock update is there, okay, so you clock update, okay, kernel initialize, and then you call thread new. Okay, so thread new, you can have a few of them, okay, depending on how many threads you want to create in the beginning. Okay, and until this point, it is still single threaded. Now, the moment I call OS kernel start, okay, this is where I go to the multi-threaded environment, start the multi-threading. Okay, and you do not expect to come back to the main after that. Okay, but just for a safety net, they have a while one loop here or infinite loop here, just as a safety net. Okay, but you are not coming back to the main at all once you say OS kernel start. So once OS kernel start, what happens? You are in the multi-threading mode. In the multi-threading mode. So once you are in the multi-threading mode, what happens? Okay, your scheduler will kick in. Okay, your scheduler comes in. Okay, now your scheduler is the main guy. Okay, the main manager who is going to look into the threads that you have and starts to execute them. Okay, so right now, okay, let's come to the lab over here. So in the lab setup, okay, the first thing you need to do is you need to create a follow the same thing. Only thing is I'm going to call it LED red thread. All right, so I'm going to create OS thread new LED red thread. Okay, so when you call OS thread new, you can see that I'm passing 3 parameters. What are those 3 parameters? Okay, that is where you're coming back to this. Okay, so you can just do a search if you want, or click here. All right, then you can see that I have OS thread new. Okay, so under OS thread new, okay, you can see that I pass in 3 things. The actual thread function, okay, pointer that is passed as a start argument. That means if I want to pass in any arguments, or if I want to have any attributes. Okay, these things we will look at it in the next lab. All right, for now we're not going to pass in any argument, we're not going to change any attributes, we're going to leave everything as default. So all we need to do is to pass in the thread function name. Okay, so that is what we are doing here at this point. So we're just passing in the name of the thread. Okay, so when we say OS thread new, what we are telling is we are now creating a new thread called LED red thread. Okay, so as far as the scheduler is concerned, it now sees a LED red thread. Maybe I should use red. LED red. Okay, as a thread. It has been created. Okay, now once that is done, what happens? When I say OS kernel start, I go into multi-threading mode. So when I go into multi-threading mode, okay, as you can see, there is no line here that calls any tasks. Okay, so tasks are not like functions. Functions, you need to explicitly call the function for it to execute. But tasks are independent. Okay, you just create the task. Running on the task, switching, everything is handled by the scheduler and the OS. All right, so basically I've created this thread called LED red thread, okay, which is over here, which is nothing more than just going to control the LED on and off with a particular blinking rate. Okay. Now, there is no explicit call to LED rate thread. Okay. Why? Because the moment the OS kicks in, the scheduler will look at who are all the threads that I have. Okay. Currently, I only have one task, LED rate. So I'm going to make that task, and since it is ready created, it's in the ready state. So currently, if you look at it right now, okay, it is currently in the ready state. Okay, and since there is no other task, okay, you will now be able to transition to the run state. Okay, there is no other task in the system. Okay, so as far as scheduler is concerned, I have only one task which is in the ready. So by the state transition diagram, you will transition from ready to run. Okay, so you transition from ready to run. So once you start to run, what happens? Okay, you will go into the first line over here. So what am I supposed to do? I'm supposed to blink the LED, switch on the LED. Okay, so this is my own library function. Okay, yours may look different, that's fine. So I call the LED control function, I say red LED on. Okay, after it goes on, what happens? I call OS delay. Okay, this is called OS delay. Now, what is OS delay? Let's look at the online help again. Okay, so under OS delay, what do you see? Okay, OS delay, if you look at the thing here, they say delay based on a number of ticks. All right, so for now, you take it that the one tick is equivalent to 1 millisecond. All right, so when I say OS delay 1 ticks, you will 1000, you will say delay for 1000 millisecond, which is 1 second. All right, now the important thing is this. Okay, this is the very important thing here. Okay, the delay thread is put into a block state and a context switch occurs immediately. Okay, the thread is automatically put back to the ready state after the given amount of ticks has elapsed. Okay, if the thread will have the highest priority in ready state, it will be scheduled immediately. Okay, so what does that mean? That means over here, when I go to the run state, when I initially go to the run state, okay, and then I call OS delay. Okay, 1000. Okay, that means 1 second. What would happen is I immediately transition to the block state for 1 second. Okay, so if you look back at our state transition diagram, when a task goes to the block state, okay, that means it is waiting for some event to happen. In this case, the event is this 1 second interval. I need to wait for this 1 second to finish. Then only I can come out of this block state. So during the 1 second, what will happen? The scheduler, okay, will be able to now look at who else is available. Are there other tasks available that are in the ready queue that I can now let them use the CPU? Correct. So that is the biggest advantage, okay, of multi-threading system. That means you don't have to waste time for unnecessary things. Okay, in this case, your intention is to let the LED blink and wait for 1 second. So in the 1 second, I actually can automatically do a context switch to some other task and allow that other task to run and use the CPU. Okay, now the thing is, when this is happening, okay, in this example here, there is no other task. So if there's no other task, then what will happen is just going to be in a block state, okay, for the 1 second. Now after the 1 second is over, what happens? Okay, so the documentation says that after the 1 second is over, it goes into the ready state first, correct? Because there is no way to transition from block to run. When you come out of the ready, when you come out of the block, you have to go to ready first. Okay, then when you go into the ready state, the scheduler will again see whether there are other tasks in the queue. Since there are no other tasks in the queue, then from ready, you can go to run. Okay, which means that I can now come to the next line here, which is to off the LED. Okay, I'll off the LED here. So I will now go to this part over here to off the LED. Off red LED, and then I do the same thing. I call the OS delay again. I call the OS delay again for another 1 second. Okay, which means another 1 second I'm going to be delayed. I'm going to be blocked. Okay, and then what happens? It is repeating itself indefinitely. So once I finish, this is the for loop, then I come back in again. Okay, so let me answer the question first. Why do you need the for loop? Okay, which for loop are you referring to? Is it the main one? Okay, if you're talking about the main for loop, okay, the main for loop is not necessary. Okay, even without the for loop, like as you can see here, I commented it off, it still works. Okay, so again, that is just a safety net. All right, for the for loop inside here, okay, like I said before, the whole idea of embedded systems, operating systems, is you write the thread as if it is going to run indefinitely. Okay, if you remove the for loop, then what happens is the task only runs once, and after that it stops running. Okay, which is not what you want. Okay, you want this thread to keep on running indefinitely. Yeah, you can use while loop or for loop, doesn't matter. Okay, you just need to have an indefinite loop, okay, to make sure that whatever the task is supposed to do is done indefinitely. All right, so that is basically the first activity. Okay, so let's just see what happens. Okay, so as you can see, this code here is nothing else except the red LED thread. Okay, and the red LED thread is just supposed to on the LEDs, okay, at the blinking rate. All right, so let's just run this, okay, and see what happens. Okay, let me bring out my okay, so let's run this now. Okay, so as you can see, the LED is blinking, okay, as expected. Okay, going through the 1 second on, 1 second off timing. Okay, so again, this is expected, so no issues. Now let's stop this first. Okay, and slowly make some changes, and let's discuss what is going to happen. All right, so the first change I'm going to do is I'm going to replace this with this. Okay, so what is this? This is the normal delay. It's not the OS delay. All right, so in the OS delay, we saw that it goes through a context. It can go through a context switch. All right, but now instead of that, I'm going to put a delay, which is the function I think we have been using earlier on. Is just nothing more than some loop that keeps on executing some no op, okay, just to create the effect of a delay. Okay, so this value is not exactly 1 second, okay, it's slightly shorter. So you will see the delay is a bit shorter than 1 second, but the idea is giving us some delay, okay, in the typical, the usual sense. Okay, so now let's compile this first. Okay, so before I run this, maybe we can just have a sense of what you think will happen. Okay, so basically what we have done is we have removed the OS delay and place it with a normal delay. Okay, actual loop delay. Okay, so I think most of you, this is not an issue. Okay, so it's quite obvious it will be the same. Okay, so let me okay, so let's come back here and just confirm that behavior. Okay, so the same LED blinking, the rate is a bit faster, okay, because this is not exactly 1 second. All right, so I think there are no surprises here. Okay, so let's come back here now. All right, so the main difference is in the case of the normal delay. Okay, in the case of the normal delay, okay, when we say it's a normal delay, you are still in the run mode. You are not giving up the CPU. That means you are forever in the run mode. Okay, then you off. Okay, then you delay again, then you are still in the run. Okay, so your state does not change. So when your state does not change, you're always in the run mode. You do not give up the CPU, which means others cannot use it. Okay, you're hogging the CPU even when you don't really need it. Okay, so let me put this back here. Okay, so it's back to OS delay. Now let's go on to another thing. Okay, so just now there's another question about the thread creation. Okay, so you can create threads wherever you like. You don't have to do it only in the main. Okay, so one inside another thread, you can create another thread as well. Okay, there is no restriction on that. Okay, so whatever you want to start off with, the moment you go into multi-threaded mode, that is what you put inside here in the main. But along the way, you are free to create other threads that you want. Okay, now let's do this now. I'm going to now add another thread here, which is LED green thread. Okay, so red thread and green thread. Now, and now both of them are here. Okay, so if you look at the code, both of them are exactly the same code. Okay, LED red thread, LED green thread. Okay, both of them have they are on their respective LED. Both of them have the same delay, delay 1000, OS delay 1000. All right, so let's look at the sort of timing diagram for this first. Okay, so I'll not look at the main. So the main already created the LED red thread. So in terms of the main, okay, what we did is we first create LED red followed by LED green. Okay, then we OS kernel start. Okay, so now we are in the multi-threader mode. Okay, so that is the single threader. Now in the multi-threader mode, let's look at it. So we have LED red over here, and we have LED green. Okay, now we have both of these threads. All right, now, and since we use the default settings, that means both of them have everything the same, and both of them are equal priority. Okay, so don't worry about the actual priority numbers now. Just take it that both of them are equal priority. Now, when I say OS kernel start, who will run first? Will red run first or green run first? What do you all think? Is it going to be red run first or green run first? Any ideas? You can put in the chat. Okay, so red. Okay, so most of you think it's red. Okay, so if you think of the logical perspective, you created both of them, and since both of them are equal priority in terms of the queue, what will happen? So if you look at the scheduler queue, okay, in terms of the scheduler queue, what you will see is, you will see that the first person in the queue is red, second person in the queue is green. Okay, so this is the queue. So the scheduler always maintains a queue of all the tasks that are in the ready state. Okay, so whichever task came to ready state first would be the first in the queue, followed by the next, and so on. Okay, and since there is no difference in the priority, then they will go in the order in which they were created. So red will be the first in the queue, followed by green, okay, and so on. So we know that, okay, we have two tasks in the ready queue, and both of them are equal priority, correct? Now, when I start to run, okay, what is going to happen? Because it's going to happen. So let's give me a minute here. Let me clear the whole. Okay, so let's run this poll again and tell me what you think will happen. Okay, think carefully. Okay. So you have both the tasks. Okay, we know red created first, green created second. Okay. Okay, don't worry about the responses from others. Not always the majority is right. Okay, I'll give you a bit more time to think. Okay, I think nobody else is responding. All right, so basically you split into 1 quarter and 3 quarter. All right, where 1 quarter is thinking that is on off for red, then followed by on off for green, and then we repeat. Okay, 3 quarter of you think that red and green both on together, followed by red and green both off together, and then we repeat. All right, so let's okay, let's clear this. Okay, so let's look at our code again. All right, so both of them, all right, and both of them are created. So let's let me build this and we'll see what happens. Okay, let me bring out my camera. Okay, so let's run this. Okay, so it's quite bright. Okay, but basically you see it as yellow, right? You see it as yellow. That means both red and green on together. Okay, followed by red and green off together. Okay, so why do we see this? Okay, so let's look at what is happening. So in the very first case, what happens is actually the red does run first. Correct. So the red runs first, it does switch it on. Okay, so there will be a time where only the red is on. Okay, okay. When you step through the code, you will see. Okay, later I'll show you. But what happens after that? The moment you switch it on, okay, you go and say you delay. Okay, delay for 1 second. Correct. And the moment I delay, okay, so initially you have to remember that this is in the run state. Okay, whereas the LED green is currently in the ready state because it is waiting for its turn. Okay, it's waiting for its turn. But the moment you say delay, what happens? You go to a block state here. Okay, you go to a block state. Okay, you go to a block state. So when you go to a block state, what happens? Okay, you are allowing a contact switch to happen. So when I allow a contact switch to happen, then the LED green will now have a chance to go to the run state. So you will now say switch on and you will say delay. And then you also go to a block state. Okay, so there will be a period of time where both of them are in the block state. Okay, but okay, since the delay is the same, both 1 second, 1 second, and red thread call that delay first, you will also be the first one to come out of that 1 second, correct? Okay, so when it comes out of 1 second, you'll be switching off the LED. So you will again observe, okay, if you step through the code, there will be a period of time where after it off, where only the green LED is on, green on alone. Okay, but again, it's so short that you can't really see it. Okay, only if you step through the code, you can see it. Okay, so after it goes off, okay, then it calls for another delay. Okay, and then there will be a slight time before this task comes out of the block state. Okay, then it's able to do the run. You go to the run state and you will do the off, and then you will also do the delay. Okay, and then the whole process will keep repeating. Okay, so it is going by sequence. That means red is on first, followed by delay. But because it is very fast, you don't get to see the red on. Okay, but so the moment the red is on, the contact switch happens with the delay, and the green also is on, and that is why you see it as having that yellow light display there. Okay, so that is what is happening over here, and I think we can explain that, okay, with the idea of the switching. Now let me just do one more thing here. Okay, okay, so okay, now what I'm going to do, I'm going to do something else here. I'm going to change both of it with the normal delay. Okay, so the thread creation part is both the same. Okay, no issues, no changes with that. But both for the red LED thread and the green LED thread, I have replaced both the OS delays with the usual for loop delay. Okay, both of them with a for loop delay. All right, so now what do you think will happen? Okay, let's run a poll again. Let's see what you think. Okay, so both the delays now replaced with instead of OS delay with normal delay. Okay, think carefully. Based on what we understand so far, if there is no OS delay, that means is there going to be a context switch happening? All right. Okay, so in the interest of time, I will just take it as this first. All right. So majority of you are taking option one. That means the LED red is going to be hogging the CPU, so it's just going to be red all the way. All right, and there's no context switching. Okay, then there's a quarter of you who think that it's going to be red first, followed by green and red and green and so on. Okay, so let's end the poll here. Okay, now let's come back to our code here. Okay, so this is our code. Both of them having the normal delay. Okay, not the OS delay. Let me build the code. Okay, so let's look at our. Okay, so let me run it first. Debug mode. Okay, so this is the moment of truth. Moment of truth. Let's see what happens. It is still yellow. It is still yellow. Okay, even though I have changed my OS delay to normal delay. Okay, this is strange, right? This is strange. It should not be the case because from our understanding, you should be hogging the CPU, correct? The red should be hogging the CPU, but apparently it is still having a context switch with the exact same behavior as just now. All right, it seems to be having the exact same behavior as just now. All right, that means the moment I on, I switch, I on, I switch. So how come it is still having a context switch? All right, even though I'm using normal delay. All right, so that is something unique, okay, to the RTX RTOS. All right, where if you look under this file here, rtx config.h, there is this thing called OS round robin enable. Okay, so this is the default setting, okay, for the RTX OS. Okay, and what it does is for threads that are equal priority, okay, for threads that are equal priority, okay, that do not that are in the ready state, okay, what they will do is what the scheduler does, it does a round robin scheduling among all the threads that are in the ready state. Okay, and that is for every 5 ticks. And so every 5 milliseconds, it will actually does a round robin. Okay, as long as the tasks are in the same priority and they are all in the ready state. Okay, so what is happening here is it is not now. Okay, it is not you're doing a normal delay, but you're not going to a block state. You're not going to a block state. But what it does, it is now continuously doing a switch here and here and here and here every 5 milliseconds. Okay, so every 5 milliseconds, it is constantly switching between the two tasks from the beginning because they are both in the ready state, okay, and they are both of equal priority. So this is something that is unique to RTX. Okay, not all OS does this, all right, but RTX does this, and I think it is actually a good way of managing its resources, all right, because if you think about it, they are both equal priority, means they both want to share the CPU, correct, and they are both ready, correct. There is no issue that they should not run in parallel. All right, so this feature by RTX is actually something that is good, that allows equal priority tasks that are ready to actually run and use the CPU. Okay, so let me just show you if I were to change this to 0. Okay, if I were to change this to 0 and I come back here and let me save this first. Okay, and then I build my code. Okay, and then I will run, go to debug here. Okay, and now if I run, you will see that it's only red. Okay, because now it is hogging the CPU because we do not allow any round robin switching. Okay, so only red is happening, but by default, okay, the round robin is enabled, which allows equal priority threads to share the CPU. Okay, so this is something interesting. The round robin is there by default and it will be enabled by default. Okay, so do not change it. Okay, for the lab alone, I just give you instruction to change it just for you to see what happens. Okay, but always keep it enabled at all times because that allows you to fully utilize and share the CPU across tasks which are equal priority. All right, so it's good to keep it enabled all the time. All right, but in the lab, you just do it just to see what happens. Okay, so you can see that you get a sense of the different behavior of the sort of OS under different circumstances. So we will be looking into this in more detail in each of the subsequent lectures and the labs and so on. All right, so for this week's lab, when you try it out, just see the behavior for yourself, try to make sense of it, go back to the state transition diagram and try to understand which state you are in, what is the transition that is happening and so on. All right, so don't just look at the LED, but try to link it back to the state transition and possibly draw this kind of a timing diagram so that you can understand what is happening, okay, where I am, what was I doing, which state was I in, and so on. Okay, and in the lab, okay, when you are doing it, all right, you can also put some breakpoint. Okay, so you can put a breakpoint maybe in the delay over here and in the delay over here, the first delay. So you can actually see the sequence. That means that the LED is first on, followed by the green. Okay, then only you see the yellow. And similarly in the off, the LED goes off first, then you see the green for a while, then the green goes off. Okay, so you can put a breakpoints in the LED, the delay function there, just to see this happening as well. All right, so I think, yeah, that's all I have for today. So if any questions, you can ask me. If not, I'll see you all in the lab on Friday. Okay, so the round robin concept is basically, as long as you have tasks of equal priority and those tasks are in the ready state, then the OS will allocate a round robin sequence among all those tasks. So in this case, we only have 2 tasks. So both these tasks will switch among each other every 5 milliseconds because they are both considered equal priority. Okay, so in the case where the first instance, okay, where this context switch is happening, if your 5 milliseconds is if this first part of the code here is greater than 5 milliseconds, then you might have already done a context switch here. Okay, but from what I've done so far or tested, this part is before 5 milliseconds, so the delay happens. All right, and then from the block state, you do a context switch. Now, when you are already do the context switch, you are already again switching on and do the delay. So after the delay, you are also going into the block state here. So both of them are going to be in the block state. All right, so the context switch that happens in the first instance with the OS delay is because of the block state. Okay, but if it happened to be that your first part of the code here is longer, you're doing other things, then before the 5 millisecond itself, you can have a context switch to the other task. Okay. What did you change to get the? Okay, so when we are using OS delay, okay, there is nothing to change. Okay, so for OS delay, the RTX config by default here is a 1. OS Robin enable. Okay, so under RTX config, here the first file here, the fourth file here, the default setting is 1. So if you keep that as 1, then the round robin will happen. Okay, but in our case, for the first one with the OS delay, okay, the context switching happens because of the OS delay. Okay, so the OS delay triggers the context switch, which allows the red and green to light up together. Okay, but in the case where we use the normal delay, the context switching is happening because of the round robin. Okay, when round robin is there, you can have context switching in both cases, either timeout or either blocked. Both can trigger a context switch.
Sorry, but for the example that you showed just now, is it because of timeout or block? Or is it?
When it is the OS delay, it is because of the block.
Okay.
And it is without OS delay is because of the context switch, because of the round robin.
Oh, okay. No, quite a bit confused because in the slide.
Sorry, give me a minute.
Yeah. Okay. Because in the slide, right, the state transition, then it seems like to go from running to ready again, it's either through timeout or block. So I'm just curious about just now the example you showed just now, using the delay and then 2 equal priority threads. Does it go through the timeout?
Okay, so
or block?
It can go through both. Okay, so a context switch can occur based on 2 ways. One is the block, all right. The other is the timeout. So by default, the timeout is there. That means if I have 2 tasks, okay, T1 and T2, okay, both of them that are running, okay, I say both are initially ready, and both are ready here, and this is run, switch to run first. Okay, if within the first 5 milliseconds, okay, let's say within the first 5 milliseconds, there is no blocking call. That means it can run all the way. Then what will happen is there will be an automatic context switch.
Okay. Oh, so the round robin that 5 milliseconds is somewhat like this timeout.
Yes.
Okay.
That is always there. So as long as both of them are the same priority and both of them are ready, that 5 millisecond context switch will definitely happen. Okay. But in the case where there is a call, there's a blocking call somewhere and there is a change of state and it goes to a block state, then you have a context switch earlier on.
Okay. Yeah. You just now you said the round robin thing is quite specific to the RTX. But assuming like I guess the regular RTOS, what kind of scenarios will cause timeout? What kind of
timeout as in what?
Like for other kind of RTOS systems, what are like the scenarios that cause a task to time out?
Okay, usually in the OS context, you have to program, you have to explicitly put a timeout yourself, like the OS delay.
Oh, I see.
That means if I'm in a similar situation, if there is no context switching, like what we saw, okay, so assuming there is no more context switching, correct? in other OS,
yeah.
then a task that is running will be running forever until it goes to a block state. Okay, so if it doesn't go to a block state, then T2 will never get a chance to run.
Okay.
So you need to explicitly put in some areas where you want to purposely go to some delay to allow another task to run.
Okay. Also, timeout is something like we can control, but block state is something like system resources controlled by it. Okay.
Yeah.
Thank you.